Okay, so let me first remind you about, so we'll be looking, so last time, then we were looking at, we had a sequence of functions on an interval I, and we have a function f on that same interval. And then we talked about two notions of convergence. One was the pointwise convergence. So this meant that, so we say that this sequence converges to f pointwise if for all x fixed, you're looking at the sequence fn of x, right? So x is fixed, and that this here converges to f of x. Right, so that was the pointwise convergence. And the second convergence that we talked about was a uniform convergence. So this is two uniform convergence. Right, and so we say that this sequence here converges to f uniformly if for all epsilon greater than 0, there exists an n, so that if you're further out than n, then the difference between fn of x and f of x is smaller than epsilon, and this here has to hold for all x. Right, and so again, uniform refers to that is for all x. Right, so it's uniform in x. Okay, and so there was one example that was particularly illuminating, and that was that we took, so if I here was the interval from 0 to 1, and if we're looking at the function fn of x, that was just x to the power n, and f of x is then the function that is 0, unless, so 0 if x here is between 0 and strictly less than 1, and 1 if x is equal to 1, right? And so the picture was that, right, so the picture was that, so that you have this sequence here. They are defined on the interval from 0 to 1. They all end up at 1. And then as n become larger and larger, these functions become more and more steep towards 1, right, like that, right? And so then we had that this sequence fn converts to f pointwise, because if you fixed x, then really these values here converge either to, if x is not equal to 1, then as n become large, they converge to 0. If n is 1, then the fn of 1 is, that's always 1, right? So it's clear that it's converging pointwise, but fn does not converge, not converge to f uniformly. Right, and the reason why it didn't converge uniformly was that we saw that for each, if we, by the intermediate value theorem, if we were looking at a half here, then for each of the function, there would be an xn, so that the value at xn was 1, right? And so, was a half, sorry, right? So you define xn so that the value of this is a half. But now if you're looking at f of x minus f of xn, like that, and if this here, sorry, is n, then this here, this difference here is actually just a half, right? And this difference here should be small. If n was sufficiently large, it should be small for all x, but it's not. We used one particular x to show that it wasn't, right? Okay, that was just a quick review of some of the things we talked about last time. Now, let's get to a theorem. And so maybe also one more thing about this example is that you see that these functions here, these functions fn, they are all continuous, right? But the limit is not continuous, right? So pointwise, so note that, that pointwise convergence is not enough to guarantee that limits of continuous functions that the limit of continuous function is continuous. Right. Okay, so that's what this example illustrates. So now instead we have the following theorem that, so we have this interval and we have a sequence fn and we have f all defined on this interval. And if we assume that that all of these fn's are continuous, and b, we assume that the convergence here, the convergence of fn to f is uniform, then the claim is that then f here is also continuous. Right. Okay, so let's try to prove that. Right, so pointwise convergence is not enough to guarantee that the limit is continuous. Uniform convergence is enough. Right. Now, let's see, so let's prove that. So, given epsilon greater than 0, there exist capital N such that if little n is bigger or equal to capital N, then fn of x minus f of x is smaller than epsilon over 3 for all x. Right, this just follows from that the sequence converges uniformly, right? So this is the first thing. And the second thing is, so this was since fn converges to f uniformly. The second thing is so now we have n. This here holds for all little n bigger or equal to capital N, but in particular it holds for capital N. So now since f capital N is continuous, so this is a fixed function now. Then given then for any fixed x0, we have that there exists delta greater than 0, such that if x minus x0 is smaller than delta, then this function, the value at these 2 points, differ at most. So this is for the Fn. The value at these 2 points differ at most by epsilon over 3. Right. So again, we have a sequence Fn, f little n, that converges uniformly to some f. We want to prove that this f is continuous. So we just need to prove that for each x0 fixed, it's continuous at x0. Right? First, I'm using that the sequence is converging uniformly. So given this epsilon, there exists this capital N, so that if you're further out, then you have this. I'm not even going to use the part that is further out. I'm just going to pick this capital N, right? And so then I'm using that this f capital N is continuous. And it's continuous at x0, so I have this, right? And so now we need to estimate. We now need to estimate the difference, right? So what we're really interested is in f, but the f capital N, that's going to help us estimate the difference between these two numbers. And so these two numbers, so x here, x0 was this fixed point that we want to show that f is continuous at that point. And the delta, well, the delta came from f capital N. So we're looking at this x, this close, where the delta was given by f capital N. And now we use the triangle inequality. So this difference here is, so you may as well think about this one here, and you could compare it with the value at the same point. So I'm just writing this difference down as a sum of things. So, and then afterwards I use the triangle inequality. So here, minus f capital N of x0. And then I'm adding back this here again, f capital N of x0. And I'm comparing this with f of x0. Right, so you see that here, this is really the same, because here I'm subtracting this thing that I didn't have, but I'm adding it back. Subtracting this thing that I didn't have, but I'm adding it back. So I'm just left with those two things, which is that. Right? And so now we use the triangle inequality, that this is now bounded by f of x minus fn of x plus fn of x minus f capital N of x0, like that, plus, and then f capital N of x0 minus f of x0 with absolute value sign, like that. Now, this thing here is smaller than epsilon over 3, and that came from that it's evaluated at the same point, and the convergence was uniform. So it really was the first part here, right? So that is less than epsilon over 3. This one here comes from that the difference between x and x0 is less than delta, and that this function fn was continuous at x0. So this is another epsilon over delta. This is this second part here. And then the last here is again the same that gave us this bound, namely that the convergence was uniform and is evaluated at the same point. So you have that, right? And so what we've proven here is that so for this given x0, if the difference between x and x0 is less than delta, then the difference in the images is less than epsilon. So this means that the function f is continuous at x0, and x0 was arbitrary. Okay. Now, now the first application of this is that suppose you're looking at the following example. Xn of x is the sum here from k equal to 0 to n of xk over k factorial. Suppose you're looking at xn like this. Then the xn here of x, they are all continuous, right? They are sum of polynomials. So, you know, they're just a polynomial, actually the sum of what's called homogeneous polynomial, but they are themselves polynomial, so they are all continuous. And Weierstrass m-test, so, and by Weierstrass m-test that we proved last time, by Weierstrass m-test, the convergence here to E, where E here is the exponential function, so it's this power series sum from k equal to 0 to infinity of x to the power k over k factorial. The convergence, this convergence here is uniform. It's uniform assuming that you do it on a compact interval. So it's uniform on any fixed interval of the form, say, minus L to L. Right, so if you're fixing an interval like this, then the convergence is uniform. And so this means that since these guys here are continuous, then it implies that this one here is also continuous. Right? So this is implied by the theorem that we just proved. Now, so now this will uniform convergence. There's another way of thinking about uniform convergence that, in a way, makes it more natural. So, remember that if we looked at, so if we take an interval, let's say that this is an interval from A to B, A and B are real numbers. Then we looked at the space of continuous functions on this interval, right? And this space had a natural metric, so I'm using here that both endpoints are included. This space here has a natural metric. And that metric is that if you take two functions, two continuous functions on the interval, then the distance between these two functions is just the max. of the max of the difference between the two functions. Right. The difference again, why is this? Why the difference is continuous? So this means that the maximum the difference is continuous. So this is a continuous function, and it's still continuous if you take absolute value. And so this means that the maximum by the extreme value theorem is achieved. Right. Right. And so this here was a natural distance between them. Right. Now to say that the sequence here, to say that the sequence f little n is converging uniformly, you can think about that in terms of this distance. So, so we have the following proposition. Fn converges uniformly to f if and only if Fn converges to f in the metric space. With this metric. Okay. Now, why is this the case? So this is just that. So proof of that. It's really just a one-liner because you see that to say that so that f of x minus fn of x is less or equal to epsilon for all x. If this here is the case, well, this is equivalent to saying that the distance between Fn and f is less or equal to epsilon for all x. Right, because if this here is the case for all x, then the maximum is less or equal to epsilon. This was the maximum. And on the other hand, if the maximum, well, then it holds for each x. Right? So this is sort of a tautology. Okay, and so now we see, of course, that if the sequence, so you have that, but this means, so this means that if the sequence, therefore, if the sequence Fn converges to f uniformly, well, then it means that for all epsilon, if we're sufficiently far out, then this here can be, for any given epsilon, if you're sufficiently far out, this here can be made less or equal to epsilon, which means that this here can be made less or equal to epsilon if you're sufficiently far out. So you see that if this converges uniformly, then it implies that this thing here converges to 0. But that's exactly what it means, that the sequence Fn converges to f in the metric space. And the other way around, if the sequence converge, Fn converges to f in the metric space, this is equivalent to saying that this here goes to 0. But if this here goes to 0, right, this means that if you're sufficiently far out for a given epsilon, if you're sufficiently far out, this here is less or equal to epsilon, but it means that this here is less than epsilon, right? So that means that it really converges uniformly, right? Okay. And that's in a way that makes it much more natural. I mean, yeah. So it's it makes uniform convergence much more natural. Okay, So now let's prove the next theorem. So for this theorem, we're going to think about uniform convergence in terms of this metric and in terms of convergence in this metric space. So the theorem is this next thing that say that if you take an interval from a to b and you're looking at the continuous function and you equip it with this metric that we talked about, then this here is this space, which is a metric space. So this metric space is a Cauchy complete. Okay. So remember, Cauchy complete in a metric space means that if you take a Cauchy sequence, so just let me just record here over here. So Cauchy, so if x comma d is a metric space, then Cauchy complete means that any Cauchy sequence is convergent. Right, that's what it means to be a Cauchy complete. And of course, an example of a Cauchy complete metric space was just if we took R with the usual metric. Okay. Now, so what we have here is, so let's try to prove this. So we need to prove, so this here is now, we need to prove that if this here is a Cauchy sequence, then there exists a function that is also continuous, and so this sequence here converging to f in the metric d. Right? That's what we need to prove. Okay. So in particular, we need to first construct a function. Right. F. Right. So now, let's try first to construct a function. So we first construct f as follows. Well, if you fix x, right? So x is something, so a point in the interval. And now look at this sequence Fn. This is now a regular sequence, right? And so, but if you're looking at the sequence, then we have that Fn of x minus Fm of x. If you have two n and m like this, then the difference here is less or equal to the max, where this is for all set in the interval of Fmn of z minus Fm of z, like that, right? Because of course, you know, I mean, it's like, in particular, if z was x, right? So you have clearly this. But now you see that, so I claim that this means, so I claim that this implies that this implies that this sequence here, fn of x, this sequence here, which is a sequence of real numbers, these here real numbers, that this here is a Cauchy sequence of real numbers. Why? Why is that the case? Well, it's the case because given, so this is just because given, so this is the case because given epsilon greater than 0, since Fn is a Cauchy sequence in the metric space, in this metric space, then there exists capital N, so that if little n and little m are bigger than capital N, then the difference between these guys, the difference between this function here and that function is less than epsilon, right? This is because they were Cauchy sequence. And so now this thing here is, of course, this thing here, that's what we just saw. This is like the maximum. So this is bigger than when you evaluate it in just one point. Like that, right? And so this proves, right, that this, when x is fixed, these guys here is a Cauchy sequence of real numbers. So now we use, since R here is Cauchy complete, and Fn of x is a Cauchy sequence, then it means that that the sequence Fn of x, that this is converging, and it's converging to some number, right? So just one number, and that number we can call f of x, right? So we just defined f to be the limit of this sequence, right? And that's well defined because there's just one number, right? So for each x, it gives you a number. Okay, so now what we have proven is that, so now we have a candidate. So namely, we have shown that, so now what we've proven here is that we have found a function. So we have now proven that this sequence here is converging to some function f. The convergence is just pointwise. And we don't know whether this function is continuous or not, right? The convergence is pointwise. This is just because it converged for each fixed x. It was f of x was defined so that it was a limit of these guys, fn of x, right? Okay, so now we need to promote this convergence. So the point was pointwise, and we need to promote the convergence to uniform convergence, right? And so So now we need, given epsilon greater than 0, again, since these guys, Fn was a Cauchy sequence, in the metric space, in this metric space, then as we saw over there exist capital N, so that if little n and little m are bigger than this capital N, then the difference between these two, then Fn of x minus Fm of x, this thing here, is less or equal to, and I'm using epsilon over 2 for all x. Okay? So you have that. But now, this here holds for all m and n. Right? Let's just fix n. And now we can use that it's still true. I can still let m vary, right? And so if you let m go, so now fix n bigger than capital N, and let little m go to infinity, right? Well, this here is just some fixed number. But as m go to infinity, this here go to f of x, right? And so since this difference is always less or equal to epsilon over 2, it's also the case that the difference here of the limit is less or equal to epsilon over 2. So you have this here for all x. Right? This is just letting m go to the limit. But this, of course, say that the max, if you will, so you have that, so this implies that the max of Fn of x minus f of x, that this thing here, where x is now in this interval, that this is less or equal to epsilon, right? But this is like the same. This here is just the distance between Fn and f, right? So say that this distance here is less than, I guess I had epsilon over 2. So it means that this thing here is strictly less than epsilon. It's actually less or equal to epsilon over 2, so it's strictly less than epsilon. But that's exactly what it means for this sequence here. So this is the same. This is the same as saying that Fn converts to F uniformly. Right? Here I should have taken the soup. The reason why I should take the soup here is that f is just a function. It's not necessarily continuous at this stage, right? So, but it was clearly the case with the soup. So the maximum a priori may not be achieved yet, but now you see that they converge. These Fn converge to F uniformly, right? But then, and these guys here was continuous, right? These here is continuous. So this implies that by this theorem we just proved that F is also continuous, right? And so you see that, so now you have that the limit is indeed in the space, and we already proved here that the convergence to this limit is uniform, which means that it's in in the metric. Okay. The next thing is that, right, so this here was just a little bit different way of thinking about uniform convergence, that you think about it sort of more abstractly as a convergence in a metric space, right? And it's a useful way of thinking about it. The next thing we want to look at is how this uniform convergence gives you a way of computing things. So in particular, if you have some power series, and we talked about that a little bit last time. We didn't prove anything, but one of the motivation for this is that suppose you take a power series like this, and we'll return to this in just a second. But suppose you take a power series like this, and you are inside the radius of convergence. So inside radius of convergence. So you know that this thing here makes sense, right? That this for each x gives you a number. And so it gives you a function, and so you're interested in what is the derivative of that function, and what is the integral of that function? How do we integrate it, and how do we take the derivative? And the thing that worries you a bit is that if it was just a finite sum, it would be trivial, but it's an infinite sum, right? And so is it okay? So the natural question is it okay if you want to take the derivative, can you interchange this infinite sum with taking derivative? And likewise, if you want to integrate this infinite sum, is it okay to interchange the infinite sum with taking the integral? And the answer is it's okay. Okay, and so let's see that. So if we do this, so we have two versions of this, one that's dealing with taking integrals, and another version that deals with taking derivatives. Okay. And so the first thing is that I take, so the first theorem is the following, that I have some interval from A to B, and then I have a sequence of functions, Fn, that are integrable. They may not be continuous, they're just integrable. So in particular, they are bounded. And then I have that Fn here converts to F uniformly. Okay. And I want to prove that, so the claim is that F here is also integrable, and the integral of F is equal to the limit of these integrals. Okay. So in particular, of course, those integral here has a limit, right? It's part of the statement. Okay. Right, so now, right, so what do we need to prove? So prove. remember that, so we want to show, so we first want to show that f is integrable. And we had a criteria for doing that. So we're using the criteria, so we can use that all we need to show is the following, that given epsilon greater than 0, there exists a partition P of the interval from A to B, so that the upper sum of f with respect to this partition minus the lower sum of f with respect to the same partition, that this thing here is less than epsilon. Right? That's all we need to prove. We need to prove it for each epsilon. We need to prove that there exists a partition. Right? So if we have that, then we already know that then f is integrable. Okay, and then so that's just achieved this first task, and then afterwards we need to prove that. Now,